All right, so let's walk through activity 3.5.1. I'm assuming at this point you've tried this yourself, so if you're watching this before you try it, again, that's kind of like not getting your hands dirty before just seeing the solution to something. So I encourage you to do that. But for here, let's just kind of read through this problem. I always recommend sketching the situation. And then again, reading through, we see a spherical balloon's being inflated. So the volume's changing, the radius is changing. What it says is that the volume is changing. It doesn't say volume, so let me backtrack. It says it's being inflated at a constant rate of 10 cubic inches per second. 10 cubic inches per second. I'll tell you what my brain thought of when that came up was, oh, the units in here, inches cubed per second, is volume per time. And so again, since I've been doing a lot of calculus, because it's my job, I think that's dV dt, right? The change in the volume, inches cubed, over the change in time. And I know it's a constant 10. So this is good, so I'm gonna lock this in. I know this is gonna be related to the problem somehow. The question's asking, how fast is the radius changing? There's another key word there. How fast is a rate? And what that means is how fast something's changing, the change per unit time. So how is the radius changing with respect to time? That's what we're after in the question. Okay, so I have this, I'm looking for this, and I need something that relates the two. This is kind of what I talked about in the lecture. And so what they're after in the first question here was just come up with a function that relates the rates. Well, we know that the function that relates v and r, the two quantities, is 4/3 pi r cubed, right? And then so from here, a couple things. We know that volume is changing with respect to time, r is changing with respect to time. When we write it like this, we're saying v is a function of time, r is a function of time. We're kind of making that assumption. So here this equation is really v of t equals 4/3 pi r of t cubed. And the reason I'm using those obnoxious brackets is to let you know that we have really this inner function of v here, this inner function of r here. And the key to relating dv dt and dr dt, which are not present here, would be to differentiate both sides with respect to time. Then I'd get a new equation that has the derivatives involved. So I differentiate the left-hand side here with respect to time. What's the derivative of v with respect to time? That's just dv dt. Equals 4/3 times pi times, here I have an inner function of r with a power rule outside, so I get 3 times what was left inside squared, chain rule, times the derivative of the inner function, which is r prime of t, or we'll say dr dt. And this is exactly what we wanted. This is the equation that relates the rates, right? It relates these two rates, dv and dr dt. And so this is what I'm after. So a lot of students will circle this part, just so we don't kind of get lost in the notation, and to know you're solving for that. You want to know how fast is the radius changing. So what you can do, simplify as best you can. 3's cancel here. You get 4 pi r squared, 4 pi r squared times dr dt. I'll keep circled in green just to track the changes here, equals dv dt. Well, we know dv dt is a constant 10. That's not changing. And it's a positive 10 because it's inflating. If it were deflating, it'd be negative. But so what I'm going to do then is just solve for dr dt. So I get dr dt, the rate at which the radius is changing with respect to time, is equal to 10 over 4 pi r squared. So it depends on the radius, which makes sense if you think about it. If it's inflating by a constant air amount, the radius is going to be more slowly expanding over time, as opposed to at the beginning it'll be growing faster, right? So this is dr dt. This isn't necessarily what they just asked you, but we're just circling it so that we have it. Next question asks, which is the constant rate? I've already said it's dv dt. And so let's find and compare the rates at t equals 9 and t equals 12. So at t equals 9 and t equals 12, well, we need to know what the radius is at those points. And so do we have an equation for r? Well, we know at the instance that the, not t equals 9, but d equals 9, which is what? Diameter. So at d equals 9 then, I had read that they gave us the time. So at d equals 9, what does that really mean? Diameter is twice the radius. So that means that the radius is really 4.5 at this moment. So dr dt, you can write this at, r equals 4.5 is 10 over 4 pi r squared, so 4.5 squared. And at d equals 12, that's at r equals 6, we know dr dt at r equals 6 is 10 over 4 pi 6 squared. Now this is, I don't know the square of 4.5, it's somewhere between 16 and 25, probably close to 20. And then here, this is, 4 times 36, it's getting pretty big. But it's almost irrelevant to calculate what they are. We can find out what those rates are. But I know that the same 10 divided by a smaller number versus 10 divided by a larger number, this one's going to be smaller. And it lines up with what we know about blowing up a balloon, right? The bigger it gets, the slower it's inflating versus the beginning part. So we know that, this is the larger rate. If we call this R1 and R2, it's terrible notation, but it works, right? So we know that this is the bigger rate. So I hope that makes sense of this problem. Again, just to kind of recap, thinking about units, when we say things like how fast, we're talking about rates with respect to time. Using the geometrical formula that relates the variables to hopefully unlock the rates by differentiating both sides, using the chain rule, using implicit differentiation. Solving for the rate you're looking for in terms of the other stuff, and then probably answering some questions about them. It's going to vary depending on the context, but this is the general flow to questions like this. Hope that helps.